Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where your thoughts can loosen and curiosity drifts into calm. Tonight, we'll be exploring one of the universe's most secret harmonies, the story of symmetry, how it once ruled everything, and how its gentle breaking gave rise to stars, atoms, and us. But before we begin this quiet journey, I'd love if you could take a moment to like the video and subscribe, only if these calm explorations truly bring you peace. And when you're ready, share in the comments where you're listening from and what time it is for you right now. It's always a small wonder to see this constellation of listeners, each in a different corner of time yet somehow gathered here together. Now, take a moment to dim the lights. Maybe let the quiet hum of a fan or the soft rhythm of your breathing fill the background. And as we drift into the hidden laws of the universe, remember, if your thoughts begin to wander, that's perfectly fine. Let them. They're part of the journey too. We'll still be right here, unfolding the story, one gentle thought at a time. Imagine, if you will, that far across the cosmos two civilizations rise, each on a distant world bathed in starlight. They are alike in many ways. They build homes and temples, they map the heavens, they wonder at the great machinery of reality. But there is one subtle, fatal difference between them, one they cannot know until it is too late. One civilization is built from matter, the same kind of matter you and I are made of, with atoms, protons, neutrons, and electrons. The other, in its own corner of the galaxy, is built of antimatter, a mirror image that looks, at first glance, no less stable or real. To themselves, they appear perfectly normal. Their water flows, their air is breathable, their stars shine. Yet if the two civilizations were ever to meet, to clasp hands in friendship, the touch would end not in greeting, but in a sudden flash of pure annihilation. Every particle of matter would collide with a partner of antimatter, vanishing into light. No monuments, no archives, no memory would remain. Only a pulse of energy rushing outward into the dark. It is a grim thought, but also a curious one. For if both matter and antimatter are permitted by the rules of physics, if both obey the same equations, why is it that in our world, the one you and I inhabit, only matter remains? Where are the antimatter galaxies, the antimatter planets, the antimatter civilizations, glowing quietly on the other side of the sky? In principle, they could exist. Yet when we look out across billions of light years, all the signals we receive are the same. The stars burn with matter's light. The galaxies are shaped by matter's gravity, and nowhere do we see the telltale signs of vast antimatter realms. This imbalance is not small. In fact, it is one of the deepest mysteries of modern science. According to the best models, the birth of the universe should have created matter and antimatter in nearly perfect balance. Every proton should have come with an antiproton, every electron with a positron, every neutron with an antineutron. If this were the full story, the two would have simply cancelled out, annihilating each other in the first moments after the Big Bang, leaving behind a universe filled only with light. No stars, no planets, no sleeping minds to ask these questions. And yet, here we are. Somehow, a sliver of matter, just one particle in a billion, escaped annihilation. That fraction sounds almost laughably small. 1 in a billion. And yet it was enough. Because after nearly every particle found its mirror and vanished in fire, the thin remainder gathered, cooled, and began its long journey of becoming. Those few particles clumped into hydrogen, into helium, into the first galaxies and the first stars. They cooked heavier elements, seeded planets, and eventually became the chemistry of life. Every breath you take, every stone on Earth, every distant mountain ridge on Mars, all of it is the legacy of that narrow escape, that tiny imbalance hidden in the early rules of nature. How could it be so? What secret preference? what small tilt in the cosmic dice allowed matter to win? And if there was a tilt, why does it not show up in most of the experiments we perform? For almost every force we know, gravity, electromagnetism, the strong force, matter and antimatter appear to be treated as equals. The equations behave as if there were no difference at all, as if the universe should still be perfectly balanced, ready to collapse into nothing but light. Yet, in the weak force, the least obvious, the quietest of the four, something unusual stirs. The weak force treats matter and antimatter unequally, and in its subtle breaking of symmetry we glimpse a reason why our world did not vanish into photons long ago. But before we reach those experiments, before we watch mirrors fail and symmetries bend, let us pause and recognize the quiet elegance of symmetry itself. For the universe does not reveal its rules through thunder or proclamation, but through patterns, reflections, rotations, repetitions that echo across art, mathematics, and physics alike. To understand why matter survived and why antimatter faded, we must first learn to see these patterns and to notice the rare and precious moments when they fail. So tonight, as you rest here in the quiet, we will drift through the story of symmetry, its beauty, its hidden conservation laws, its fragility, and the broken reflections that gave rise to us. We will follow Noether's insight, walk alongside neutrinos that refuse to mirror, and return to the earlier seconds of the universe when cooling turned perfection into fracture. And through this gentle unfolding, you may find yourself feeling the rhythm of these hidden rules, not as equations written on paper, but as lullabies whispered by the stars. If you step back for a moment, perhaps closing your eyes as you listen, and imagine the early universe not as a grand explosion but as a quiet sea of particles, you may begin to sense just how unlikely your existence truly is. In those first fractions of a second, matter and antimatter were born in what seemed like a perfect balance. For every proton there was an antiproton, for every electron a positron. Each mirrored the other so faithfully that it seemed inevitable they would find one another and cancel out, leaving nothing behind but a sea of light. And indeed, that is what almost happened. Almost. The odds, when you hear them expressed, sound absurd. Out of every 1 billion matter particles, only one did not find a partner. One survived. The rest annihilated in a brief blinding cascade that converted nearly all substance into radiation. That is why the cosmos today glows not only with the light of stars, but with the faint afterglow of that annihilation. The cosmic microwave background, a bath of ancient photons that fills every corner of the sky. These photons outnumber atoms by about 1 billion to 1, a quiet census etched into the very fabric of the universe. When cosmologists measure this ratio, they are not just tallying photons, they are listening to the faint echo of a primordial imbalance, the record of matter's narrow victory. This number, sometimes called the baryon to photon ratio, is around 6 times 10 to the minus 10. If written plainly, it seems like an abstract string of digits. But when spoken softly, it is the story of a survivor in a crowd of billions. Imagine a stadium filled with people so crowded you cannot move, and then imagine that, when the event ends, all but one person vanishes in an instant, leaving only a faint hum in the air where the rest once stood. That lone survivor, small and overlooked, would carry the memory of the entire gathering. In the universe, that 1 in a billion surplus carried the possibility of stars, planets, oceans, and life. Without it, there would have been nothing to see, nothing to ask, nothing to fall asleep beneath. And so we live inside the consequences of this delicate imbalance. Every breath you take, every stone you touch, every page turned in a book is made from that sliver of matter that slipped through the sieve of annihilation. It is easy to think of the cosmos as vast and inevitable, but in truth it is fragile, born on the edge of disappearance. If the balance had been perfectly exact, If there had been no preference at all, there would be no galaxies strung across the sky, no warmth of fire, no slow heartbeat of a planet carrying life. There would only be photons racing endlessly, cold and silent, a universe without witnesses. When cosmologists study the sky, they find that this imbalance is written into its very glow. The cosmic microwave background, discovered by accident in the 1960s by two engineers adjusting their radio antenna, is more than static. It is a fossil, a photograph of the universe when it was only a few 100,000 years old, long before stars had kindled. In its gentle uniformity, with only slight ripples, it whispers of the 1,000,000,000 imbalance. It tells us that the excess was tiny but real, that matter did indeed survive, and that all structure grew from it. But this raises a question, one that haunts physics even today. Why was there any imbalance at all? Why should nature have tilted its scales, even by such a thin margin, in favour of matter? The laws as we know them seem impartial. Electromagnetism does not distinguish between electron and positron. The strong force binds quarks and antiquarks with equal loyalty. Even gravity pulls on matter and antimatter with the same hand. It is only in the weak force that the first cracks appear, the first sign that nature is not perfectly mirrored. Yet the amount of violation we can measure in our laboratories seems far too small to explain the cosmic excess. Somewhere, perhaps in the first instance of the universe, the rules bent in a way we do not yet fully see. This puzzle is more than academic. It is a reminder that our existence is perched on something fragile, a sliver of imbalance that has not been fully explained. It is as though you discovered that your entire house rests upon a single crooked stone, and though it stands firm enough for now, you cannot help but wonder why the stone is there and what hand placed it. Theories abound, from hidden particles to new phases of matter, from grand unifications to the whispers of neutrinos, but none has yet given us a complete answer. And so we are left with awe that 1 in a billion could be enough, or that from such slender odds an entire cosmos could rise, or that when you touch your hand to your chest, feeling the rhythm of your heartbeat, you are feeling the echo of that narrow survival. Each atom inside you is a veteran of that primordial battle, carrying the memory of imbalance, carrying the reason why something exists rather than nothing. As you listen, you might feel the quiet strangeness of it settle around you, the sense that the universe did not need to contain anything at all, and yet it does, abundantly so. That abundance rests on a secret tilt, a hidden breaking of rules, a crack in the mirror of symmetry. And as we drift deeper into this journey, we will begin to look more closely at what symmetry means, why it appears so often in the patterns of nature, and why its gentle fractures gave us a world. For now, simply rest in the knowledge that you are here because of a sliver, a survivor, a 1 in a billion excess that quietly triumphed against the void. When you first hear the word symmetry, perhaps your mind does not leap to mathematics or physics at all, but to something much closer, much gentler. The quiet moment when you look into a mirror and see your own reflection gazing back at you. There is a kind of comfort in it, the sense that the world has folded in half and given you a perfect partner. Even though the reflection is not quite real, letters are backwards, movements reversed, it still feels like a faithful echo, a silent reminder that patterns can be trusted, that forms can repeat. In everyday life, mirrors are not the only place where symmetry hides. Step outside in the winter, and if you're lucky enough to see snowflakes drifting down, each tiny crystal reveals its own story of repetition. A snowflake turns and turns, and no matter the angle, its arms branch with astonishing consistency, sixfold symmetry etched in ice. They fall in silence, each one carrying a small lesson. Nature often repeats herself, not out of monotony, but out of an underlying rhythm that feels both inevitable and soothing. Or listen to music, and you will notice that the melodies you love most rarely wander aimlessly. Instead, they return, repeating phrases, echoing rhythms, balancing one line with another. A repeated note or a mirrored phrase does not make a song boring. It makes it whole, grounding the ear so that when change does arrive, it feels meaningful. Symmetry in music is less about geometry and more about memory, but the principle is the same: balance, return, harmony. If you look more closely at the living world, you will find symmetry woven into bodies and blossoms. The human face, with its 2 eyes, 2 ears, and the bridge of a nose in between, is never perfectly symmetrical, yet it strives for that balance, and our minds are drawn to it. Most creatures we know share this bilateral design: 2 arms, 2 legs, wings spread evenly, fins fanning left and right. For animals that move, symmetry is not just pleasing but practical. It balances weight, steadies movement, and allows forward motion. Plants too carry this rhythm. Flowers often open with petals arranged in rotational order, each petal a partner to another, circling a centre. Daisies radiate outward with a steady grace, and lilies, tulips, and roses follow patterns that seem almost mathematical in their arrangement. Beneath the waves, sea stars extend their arms in radial repetition, and shells coil in spirals that preserve proportion across growth. In every case, symmetry reassures the eye, as if life itself has agreed upon a set of rules for beauty and function. Even the built world reflects this instinct. Walk through the courtyards of ancient temples, and you will see columns lined in repeating order, arches balanced on either side, domes centered to guide the gaze upward. Architects have long known that symmetry creates calm. It grounds a structure in a sense of stability. The Taj Mahal in India, with its mirrored sides and reflected pool, does not only impress with grandeur but soothes with balance, offering the eye a restful journey. The same is true of the Parthenon in Greece, with its evenly spaced columns, or of Gothic cathedrals whose stained glass windows radiate like flowers. Human builders echo the patterns they see in nature, shaping stone and glass into repeating rhythms that comfort and inspire. Why should symmetry be so deeply woven into our perception of beauty? Perhaps it is because symmetry offers reassurance that the world has an order, that it can be trusted to hold itself together. In a landscape filled with unpredictability, storms, shadows, the randomness of daily events, symmetry gives us a place to rest. It whispers that not everything is chaos, that within the larger weave of existence there are rules that hold. Of course, not all beauty is symmetrical. The charm of a crooked smile, the elegance of a tree twisted by wind, the character of a melody that refuses to return to its starting point. All of these remind us that imperfection can also be delightful. Yet even here, asymmetry has meaning only because we recognize the symmetry it resists. To notice imbalance, one must first know balance. In this way, symmetry is not only an aesthetic idea, but a lens through which we make sense of the world. It is why children fold paper and cut snowflakes, why dancers mirror one another on a stage, why we feel a sense of peace watching ripples radiate from a stone dropped into water. Our brains are tuned to find repetition and reflection, and when we find them, we feel at ease, as though the universe is gently nodding back at us. But beneath these everyday examples lies something deeper. The reason symmetry feels so universal is because it is universal. It is not only a feature of mirrors and melodies, but a principle written into the very laws of physics. When a snowflake grows in balanced arms, when a star forms in a roughly spherical cloud, when a crystal aligns its atoms in repeating lattices, it is not merely by chance. It is because the forces guiding them are themselves symmetrical, obeying patterns that repeat no matter where, no matter when. Symmetry is not just an artistic flourish of the cosmos, it is its foundation. And so, as we drift from the snowflake in your palm to the galaxies spiraling far beyond, we carry with us this simple observation: repetition, reflection, rotation, rhythm. They are everywhere, soothing not only to the eye and ear but to the mind that longs for order. This is our first step into the hidden rules of the universe, a step that feels familiar because it is built from patterns you already know. In the sessions ahead, we will explore how mathematicians like Galois uncovered the abstract skeleton of these patterns, and how physicists learned that symmetry is not only pleasing but powerful, responsible for the conservation of energy, momentum, and charge. For now, rest in the calm that symmetry brings, like a melody that returns home, or a snowflake that lands without breaking its perfect rhythm. If symmetry in snowflakes, faces, and melodies is a comfort to the senses, then symmetry in mathematics is a deeper comfort to the mind, a whisper that even in the most tangled problems, there might be a hidden rhythm waiting to be uncovered, and few stories capture this truth more poignantly than the brief and burning life of Évariste Galois, a young man whose name you may never have heard, yet whose ideas shape almost every corner of modern science. Galois was born in France in 1811, and from the beginning his life seemed to move with unusual intensity. He was not destined for calm or safety. His years were short and filled with both brilliance and conflict. As a teenager, he began to see patterns that others had missed, glimpses of a hidden structure connecting equations that had puzzled mathematicians for centuries. For generations, thinkers had wrestled with the question of whether every polynomial equation could be solved neatly, using formulas like the ones we still learn in school for quadratics. For some, like quadratics, cubics, and quartics, there were beautiful solutions. But beyond that, for higher powers, no one could find a pattern. The search stretched on, problem after problem, like a labyrinth with no visible exit. Galois, barely in his teens, recognized that the key was not in trying to find new formulas, but in looking at the symmetries hidden inside the equations themselves. He began to imagine transformations, ways of shuffling solutions, rearranging roots that left the structure unchanged. Instead of asking, "What is the answer to this equation?" he asked, "How do the answers dance with one another? What patterns remain when they are shuffled?" This was a profound leap, the kind of sideways thinking that shifts the entire landscape. From these thoughts grew what we now call group theory, the study of sets of symmetries, the invisible skeleton beneath mathematics. To understand it, you don't need to wrestle with symbols. Imagine instead a square sitting on a table. You can rotate it 90 degrees, 180, 270, or flip it across diagonal, and in each case the square still looks the same. Each of those transformations is part of a group, a set of moves that preserve the object's structure. Galois realized that equations, though abstract, had similar groups of hidden moves. Their solvability was not about brute force calculation, but about whether the group of their symmetries was simple or tangled. It is difficult to overstate the boldness of this insight. Mathematics in his time was still a field of direct calculation and geometry. To jump into abstraction, to speak of invisible patterns that no one had yet named, was like stepping off a cliff and trusting that the air itself would hold you. And Galois did this not in the safety of decades-long research, but in the flash of youth, writing his discoveries down in haste, even on the night before a duel that would end his life at only 20 years old. He spent that final evening filling page after page, trying to preserve for the future what he had uncovered. When he died, struck down before his ideas could fully mature, his notes seemed almost like a riddle, fragments of a vision that would only later be pieced together by others. And yet, from those fragments, an entire language was born. Group theory has since become the foundation of modern algebra, a way of understanding symmetry, not just in equations, but in nature itself. Physicists would come to realize that the fundamental forces of the universe, electromagnetism, the weak and strong nuclear interactions, are themselves expressions of symmetry groups, patterns of transformations that keep the equations consistent. The particles that carry these forces, like photons and gluons, are guardians of these symmetries. Without group theory, we would not have the standard model of particle physics. Without Galois' youthful insight, the scaffolding of modern science would be missing its hidden beams. And yet, despite all this technical power, the essence of group theory can still be described in very simple terms. It is the recognition that when things change, some part of them can remain unchanged. It is the dance of transformation without loss of identity. It is the echo of a melody that shifts keys but still feels the same. The way a snowflake can spin and still carry its six-fold design. The way your face in a mirror is reversed but still recognizably yours. Galois simply gave us the tools to describe these patterns with precision. There is a bittersweet quality to his story. He never lived to see his work unfold, never saw how physicists would carry his insights into the heart of matter, never knew that his name would become shorthand for one of the most profound ideas in mathematics. But perhaps that too is fitting. Symmetry is about what remains even after change. And though Galois the young man vanished too soon, his ideas remained, carried forward like a repeating pattern, unchanged by time. As you drift with this story, you may feel a strange calm in knowing that even in the chaos of equations there is hidden order. Behind every problem that seems unsolvable may lie a symmetry, an invisible rhythm that explains why some paths are open and others are closed. And behind every symmetry, there is a quiet reminder that the universe itself may be guided not by brute force, but by patterns that are elegant, enduring, and unseen. From mirrors and snowflakes, we have now stepped into the realm of groups and transformations. Next, we will see how these mathematical symmetries connect to physics more directly, through a principle that at first seems almost playful, that nature, in all her complexity, is a little lazy. This is the principle of least action, where the rules of motion and energy emerge not from pushing and pulling, but from the universe's preference for smoothness and efficiency, as if painting with the simplest possible brushstroke. If symmetry is the quiet skeleton beneath beauty, then the principle of least action is the melody that the universe seems to hum as it moves. At first glance, the phrase sounds oddly technical, a mathematician's trick rather than a law of nature, yet its meaning is surprisingly simple, and once you begin to see it, you notice it everywhere. The idea is that, given all the countless ways a system might evolve, nature always seems to choose the path that requires the least effort, the smoothest transition, the gentlest compromise between competing possibilities. It is not a rule of brute force but of elegance, as though the universe prefers to move gracefully rather than clumsily. Consider a soap film stretched across the loop of a wire. If you dip the wire into water mixed with soap and lift it out, the film that forms will always settle into the shape of minimal surface area. It does not do this because it can calculate, nor because it has a mind, but because molecules jostling and tugging at one another eventually find the arrangement that requires the least energy to maintain. Out of chaos comes efficiency, and the delicate film quivers into the form that action has minimized. Or think of a ball rolling down a slope. There are infinite tiny wobbles and paths it could take, but the one it follows is dictated not by guesswork but by a principle. Among all the possible routes from top to bottom, it follows the one that makes its journey smoothest in terms of energy. It balances speed and position in just the right way, as though guided by a rulebook that values efficiency above extravagance. Light itself obeys this principle. Imagine a ray passing from air into water. You might think it would travel in a straight line, but instead it bends, refracting at the boundary. The reason is not whimsy, but Fermat's principle. The ray chooses the path that takes the least time. This simple statement, light takes the quickest path, is just one face of the broader principle of least action. Whether it is light bending through glass, planets tracing orbits around the sun, or particles dancing at the quantum scale, the story is the same. The path chosen is not random nor maximal, but minimal. In the 18th century, Joseph Louis Lagrange and William Rowan Hamilton took this observation and transformed physics. Instead of describing forces as pushes and pulls, they described the universe in terms of action, a quantity that balances energy in its different forms. They showed that by writing down the action for a system, and then finding the path that minimizes it, one could recover the familiar laws of motion. Newton had seen the world as a clockwork of forces. Lagrange and Hamilton revealed it as a tapestry woven by a principle of economy. Nature in their picture was not a soldier marching under orders, but an artist choosing the cleanest line. This is why some physicists like to call the principle of least action the laziness of nature. It is not laziness in the sense of neglect, but in the sense of refinement. Like a painter avoiding unnecessary strokes or a composer trimming notes that clutter the melody, the universe trims away waste. The planets do not orbit by brute chance. They orbit because those ellipses are the paths that minimize action, the ones that balance kinetic energy and gravitational pull with perfect efficiency. To picture this, imagine you're walking across a field of snow. There are countless ways to cross, but without thinking, you will usually choose the path that saves energy, perhaps angling gently instead of climbing a steep drift, or following a natural groove. Your body, without calculation, finds the least exhausting way forward. The principle of least action suggests that the entire universe behaves in a similar way, not because it is conscious, but because efficiency is baked into its rules. What is extraordinary is how this principle stretches across scales. The soap film is microscopic, the rolling ball is human-sized, the orbiting planets are astronomical, and yet the same underlying rule holds. From the small to the vast, from the flicker of a photon to the sweep of a galaxy, the universe is unified by this quiet preference for the path of least action. It is as though nature has written into its script a deep respect for simplicity, a rule that binds all its actors. And yet, this simplicity is not simple in appearance. The mathematics of action involves integrals and variations, the kind of expressions that fill blackboards with dense chalk marks. But beneath that surface, the idea is easy to rest with. Nature chooses paths that are smoother, gentler, and more efficient than the infinite alternatives. It is a reminder that even when the world feels complicated, there may be an underlying ease guiding its course. In a way, the principle of least action is a cousin to symmetry. Symmetry tells us that when things are shifted or rotated, some feature remains unchanged. Least action tells us that when things move, they do so along the smoothest possible path. Both principles express elegance, and together they hint that the universe is not a machine clanking in chaos, but a carefully tuned system whose rules are beautiful at their core. As you let these thoughts settle, you may find it comforting to imagine that the laws that govern your steps, your breath, the flicker of your eyelids, are part of the same melody that guides the stars. You're not separate from this economy of effort. Every time you choose the gentler path, every time you arrange your day in a way that feels natural, you are echoing the principle that has shaped the cosmos from its birth. And just as symmetry will soon lead us to Emmy Noether, the mathematician who revealed how every symmetry implies a conservation law, so too the principle of least action will lead us to the realization that the universe's elegance is not decorative. It is foundational. These hidden rules are the reason energy is conserved, momentum is preserved, and charge endures. But before we arrive there, take one more moment to rest with this picture. The universe, vast and cold, is also deeply graceful, gliding along the paths of least action, like a painter choosing the smoothest brushstroke across the endless canvas of space and time. If the principle of least action showed us that the universe prefers to move gracefully, then Emmy Noether revealed why that grace is not just an aesthetic choice, but a binding rule of existence. Her name may not be as famous as Newton or Einstein, yet in the quiet architecture of physics, she is a keystone, and without her insight the cathedral of modern science might not stand. Emmy Noether was born in Germany in 1882 into a world that did not expect women to become mathematicians. The university doors were often closed to her, and even when she finally managed to study, it was with restrictions, with people doubting her place in a field dominated by men. And yet, like symmetry itself, she remained resilient, persistent, quietly repeating her efforts until the shape of her genius could not be ignored. Those who knew her remembered her kindness, her generosity, her modesty, but also her fearless mathematics. She did not look for attention, yet her ideas would echo across physics more deeply than almost anyone else's. The heart of her contribution is something now called Noether's theorem. At first glance, a theorem might sound like another dry entry in the ledger of mathematics, but this theorem is more like the key to the ledger of the cosmos itself. What Noether showed was that every continuous symmetry in nature carries with it a conservation law. The universe does not allow symmetry to exist without consequence. It writes it down, carefully, like a cosmic accountant who refuses to let anything slip. Think for a moment of walking across a room. You might notice that the rules of physics do not change as you take each step. Gravity does not weaken by the window. Momentum does not vanish near the chair. The uniformity of space, its translational symmetry, means that the laws remain the same everywhere, and from this sameness comes the conservation of momentum. Momentum is not simply a human definition, but a natural accounting. When symmetry says that space is uniform, the universe balances the books by preserving momentum. Now imagine standing in that same room and slowly turning in place. The world looks the same in every direction. The laws of physics do not favour east over west, north over south. This rotational symmetry demands another entry in the ledger. Angular momentum is conserved. It is why a spinning ice skater can tuck her arms in and turn faster, but she cannot create or destroy the spin itself. It is why planets circle their stars with such stability. And then consider time. This is harder to picture, because we are so bound to its flow. But physics tells us that the laws today are the same as they were yesterday, and the same as they will be tomorrow. This uniformity across time translation symmetry, writes yet another conservation law into the ledger. Energy is conserved. This is why a pendulum swings back and forth without gaining or losing total energy. Why chemical reactions balance their books. Why the light of a candle transforming wax into flame and heat does not conjure energy from nothing, but shifts it from one form into another. In Noether's picture, every symmetry whispers a promise, and the universe answers with a guarantee. The whisper is the pattern, space uniform, direction uniform, time uniform, and the guarantee is conservation, momentum preserved, angular momentum preserved, energy preserved. Each law of conservation that grounds our understanding of physics is not a coincidence, but the inevitable consequence of symmetry. There is something deeply calming in this realization. For centuries, conservation laws seemed like separate commandments, disconnected truths. Momentum conserved, energy conserved, angular momentum conserved, 3 separate pillars, each sturdy but mysterious. Noether showed that they are not separate at all, but different faces of one hidden principle, symmetry. The universe does not waste its patterns. Every time it repeats itself, it writes an entry in its hidden ledger, a line of balance that cannot be erased. To picture it, imagine a bookkeeper sitting at the edge of reality, carefully noting each transaction. Whenever a symmetry appears, the bookkeeper opens the ledger and marks a conservation law beside it, ensuring that the accounts of the cosmos never fall into disarray. It is not bookkeeping with ink and paper, but bookkeeping with particles, forces, and fields, balancing every exchange of energy, every transfer of momentum, every rotation of the stars. Einstein himself admired Noether's work, calling it a revelation, a cornerstone of the new physics. In fact, without her theorem, much of the progress in relativity and quantum theory would have been difficult to sustain. And yet, for many years, her recognition was limited, her name less celebrated than it deserved. Only in time, as her theorem proved indispensable again and again, did her place in history grow secure. Perhaps there is a symmetry even here. Just as the universe preserves energy, time has preserved her contribution, ensuring that her brilliance could not be erased, even if in her own era she was overlooked. Like the pattern she studied, her ideas endured, waiting to be seen clearly. As you reflect on this, it may feel reassuring to know that the solidity of the world, the way you can trust that a ball will bounce, a pendulum will swing, a star will shine, is not arbitrary. It is written in the very structure of the universe, in its symmetries and their conserved consequences. Even in moments when life feels uncertain, the cosmos itself is keeping perfect accounts. Nothing is lost. Everything is balanced. And just as Noether uncovered the link between visible symmetries and conservation laws, physicists would later uncover hidden symmetries, symmetries of the quantum world invisible to the senses. These deeper patterns do not just conserve momentum or energy, they give rise to the very charges we carry, to the particles that mediate the forces of nature, to the hum that powers the lamp beside your bed. This is where we turn next, to the invisible but essential phase symmetries of quantum mechanics and to the quiet rules that give us electricity, light, and the very stability of matter itself. If Emmy Noether's ledger revealed that the great laws of conservation flow from symmetry, then the quantum world adds another layer, stranger and subtler, where even the invisible symmetries, patterns you cannot see with your eyes, carry rules that shape the particles of existence. At this level, symmetry is not just about preserving momentum or energy, but about giving birth to the very charges and forces that hold the universe together. To begin, let's imagine something very familiar. Picture the quiet glow of a lamp on a bedside table. The electricity that makes it shine seems like the simplest of things, a current flowing through wires, a switch that closes a circuit. And yet, that glow is nothing less than the visible echo of a hidden symmetry, humming faithfully behind the scenes. What seems like a convenience, light for reading, warmth against the dark, is also a triumph of the universe's most secret bookkeeping. In quantum mechanics, every particle can be described not only by its mass and position, but also by a kind of inner rhythm, a wave-like character. The mathematics of this rhythm allows for something called a phase, which is like the offset of a wave, whether its crest begins here or shifted slightly there. To us, the phase is invisible. If you look at a wave on the ocean, you can see the height and the motion, but not the arbitrary starting point of its rhythm. Yet in the quantum world, this phase symmetry turns out to be crucial. Noether's theorem tells us that every continuous symmetry corresponds to a conservation law. And here, the continuous symmetry is the ability to shift the phase of every particle's wave function without changing the physical outcome. It may sound abstract, but the consequence is concrete. This symmetry ensures that electric charge is conserved. In other words, the reason you cannot create or destroy electric charge, the reason protons and electrons carry fixed and opposite charges, is because of this hidden quantum symmetry. The lamp glows steadily, because nature refuses to break the rule written by that symmetry. Physicists call this kind of principle a gauge symmetry. It is not just curiosity, it is the backbone of how forces arise. To preserve the symmetry, the universe requires the existence of force-carrying particles. For electromagnetism, the symmetry gives rise to the photon, the particle of light itself. For the strong nuclear force, which binds protons and neutrons together in atomic nuclei, the symmetry requires gluons. For the weak force, which governs radioactive decay, the symmetry manifests as the heavy W and Z bosons. These particles are not afterthoughts. They are the guardians of symmetry, the enforcers of balance. Without them, the universe would not simply be different, it would not hold together at all. You might imagine it like this. Picture a grand orchestra. Each instrument has its part, and the music would fall into chaos without a conductor to keep time. The gauge bosons are like those conductors, ensuring that the invisible rhythms of quantum fields remain synchronized. They are not the melody itself, but the threads of timing that keep the melody coherent. In your lamp, photons carry the electrical interactions that let electrons move smoothly through the wire. In your body, gluons hold the protons in your atoms together, preventing them from flying apart. In radioactive processes deep inside the Earth, W and Z bosons carry the weak interactions that slowly heat the planet's core. Everywhere you look, gauge bosons are maintaining the score, silent but indispensable. The beauty of this is that even the most ordinary things, lamplight, warmth, the stability of matter, are reminders of hidden symmetries. You may never see the phase of a wave function, but when you switch on a light, you're participating in its conservation law. You may never meet a gluon, but without them your body would disintegrate into scattered quarks. These unseen symmetries hum in the background, preserving the charges we carry and the structures we depend on. And just as with Emmy Noether's conservation laws of momentum and energy, these hidden symmetries bring with them reassurance. They tell us that the world is not fragile in its foundations. It is anchored by principles that cannot be broken, by symmetries so deeply ingrained that even when stars explode or particles collide at near-light speed, the accounting remains exact. Charge balances, momentum balances, energy balances. The universe plays, but it never cheats. Of course, there is also a hint of mystery. For while these symmetries explain so much, they also open new questions. Why do particles have the charges they do? Why does the photon remain massless, gliding through space forever? While the W and Z bosons are heavy, lumbering carriers of the weak force. The answers lie in deeper layers of symmetry, some revealed, some still hidden, waiting for us to unfold them. But for now, you can let the imagery rest with you. The lamp glowing on the table, electricity flowing with quiet faithfulness, photons darting like messengers of symmetry, unseen but necessary. It is not only a matter of engineering or circuits, but of cosmic law. When you see that glow, you're seeing the hum of the universe's secret bookkeeping. The same hum that has endured since the first atoms formed after the Big Bang, the same hum that will continue as long as charges exist. And so, from Emmy Noether's hidden ledger, we've arrived at a deeper rule. Symmetry does not only conserve what exists, it gives rise to the very particles that make existence possible. This is the bridge between mathematics and matter, between invisible patterns and the glow of everyday life. But what happens when symmetry fails? What happens when the universe bends its own rules, even slightly, allowing matter and antimatter to drift apart? That is where we go next, into the strange territory where symmetries are broken, and from that breaking, the very structure of our universe emerges. For most of human history, mirrors have seemed like perfect storytellers. They reflect back to us an image that looks faithful, even if reversed, a world where left and right are swapped but everything else remains intact. You raise your right hand, the mirror raises its left. You tilt your head, the reflection tilts in the opposite direction. In this way, the mirror has always seemed like an honest guide to symmetry. The laws of physics, too, were assumed to be mirror-blind, treating left and right with equal respect. Why should nature favour one side over the other? Surely, like a mirror, the universe must keep both versions equally true. And then came the winter of 1956, when Chien-Shiung Wu, a brilliant experimental physicist working at Columbia University, shattered this comforting assumption. Wu was a meticulous scientist, known for her precision and her relentless pursuit of clarity. She was already respected for her work on beta decay, the process by which atomic nuclei release electrons. when two theorists, Tsung-Dao Li and Chen-Ning Yang, proposed that perhaps the weak nuclear force might not respect mirror symmetry, it was Wu who designed the experiment to test this audacious claim. Her experiment used cobalt-60, a radioactive isotope that decays by emitting electrons. The setup was deceptively simple in its description, but demanding in execution. Wu and her colleagues cooled cobalt-60 atoms to near absolute zero and aligned their nuclear spins with a magnetic field. If the weak force treated left and right equally, then electrons should be emitted symmetrically, sometimes to the left, sometimes to the right, with no preference. The mirror image should look just as valid as the real one. But when the results came in, they told a different story. The electrons overwhelmingly chose one side. They streamed preferentially in the direction opposite to the spin, a clear and undeniable sign that the universe did not treat left and right as equals. The mirror was lying, or rather, the assumption of its perfect honesty was wrong. The weak force had broken parity, the principle that the laws of physics should be the same when mirrored. This was a shock. Imagine opening a box of shoes and finding only left shoes, no rights. Imagine walking into a ballroom and seeing all the dancers spinning in only one direction, never the other. That is what the weak force revealed. A cosmos that is not impartial, but biased. A universe that prefers left-handedness in its deepest interactions. Neutrinos, those ghostly particles that stream through your body by the trillions each second, are all chiral dancers spinning in the same left-handed way. Their mirror twins do not exist. The discovery overturned one of the most cherished beliefs of physics. Until then, parity had been treated as sacrosanct, a kind of bedrock symmetry. The violation forced physicists to reconsider what they thought of as universal rules. If nature could be biased in this way, what else might it hide? What other assumptions might crumble under the weight of new experiments? And yet, there was also something strangely poetic in this asymmetry. The broken mirror revealed not chaos, but a deeper structure. The weak force was whispering that nature has preferences, that even in the smallest interactions there is a handedness, a choice. This choice may seem arbitrary, but it is not without consequence. It opens the door to understanding why matter itself exists in the form we know. Wu's experiment also carried another kind of significance. It was a triumph of experimental genius, led by a woman at a time when her field was dominated almost entirely by men. Chien-Shiung Wu did not win the Nobel Prize for her work, though Li and Yang did, but her name remains etched into the story of symmetry and its breaking. Like Emmy Noether before her, Wu is a reminder that some of the deepest truths of the cosmos have been revealed by those who had to push hardest against the boundaries of recognition. To imagine the world after Wu's discovery, you might picture a mirror that no longer offers a faithful reflection. Hold up a left glove, and its mirrored partner should be right-handed. But in the realm of the weak force, the mirror does not supply the missing glove. It simply refuses. Only left gloves exist. This strange preference might seem small, a technicality buried deep in the workings of subatomic particles, but it tells us that the universe itself is not perfectly balanced. It has a tilt, a subtle bias, and without it, the story of matter and antimatter would unfold very differently. And so, with the Wu experiment, a door opened. Through it, physicists glimpsed a universe less symmetric but perhaps more interesting, one where rules could bend, where the ledger of conservation might contain not only strict balances but hidden exceptions. The neutrinos spinning left, the electrons preferring one direction, the mirror refusing to give us a true twin. All of these were signs that symmetry could fail. But even more astonishing revelations were still waiting. Just a few years later, another experiment would show that it was not only mirrors that lied, but that even when you combined matter with antimatter, the laws were not perfectly balanced. This tiny difference discovered in the delicate dance of kaons would hint at the reason why we are here at all, why our universe is filled with stars and planets, and not a sterile void of annihilated light. The mirror had cracked, and through the crack, deeper truths shone. The U experiment had already unsettled physics, proving that the mirror was not to be trusted. Yet if nature could play favourites with left and right, perhaps it could also draw a distinction between matter and antimatter. For decades, scientists had believed that the universe balanced those two opposites perfectly, that every particle had an identical twin of opposite charge, and that the rules treated both versions the same. If you could look at the world in a mirror and swap matter with antimatter, the scene should play out identically, like a film reel projected forward and backward with no difference. That principle was called CP symmetry. C for charge conjugation, swapping matter for antimatter, and P for parity, the mirror reflection. Together, CP seemed to restore fairness, even when one alone was broken. But the universe, once again, had a surprise. The story unfolded in 1964 at Brookhaven National Laboratory in New York. Two physicists, James Cronin and Val Fitch, were studying neutral kaons, strange little particles that emerge when high-energy collisions produce quarks of different types. Kaons are not as familiar as electrons or protons. They live fleeting lives, decaying into lighter particles in fractions of a second. Yet in those tiny instants, they serve as delicate clocks, their oscillations ticking out a rhythm that reflects the rules of nature. Neutral kaons are peculiar because they can transform back and forth between matter and antimatter states. A kaon can shift into its antikaon and then back again, as if unsure of its identity. This oscillation seemed like the perfect system to test whether CP symmetry held. If matter and antimatter were treated equally, then kaons and antikaons should follow identical rules, their dance perfectly balanced, their clocks ticking the same rhythm. Cronin and Fitch set up experiments to track these decays with extraordinary precision. They expected at most to confirm that the principle was unshaken, but what they found was unsettling. The clocks ticked differently. The neutral kaons decayed in ways that violated CP symmetry. Matter and antimatter were not mirrors of one another. The universe, at least in the strange language of kaons, showed a tiny but undeniable preference. This violation was not dramatic in size, just a subtle difference in decay rates, a slight imbalance in outcomes, but it was revolutionary in meaning. The laws of physics, it seemed, were whispering a hidden bias in favour of matter. If you imagine a cosmic coin flip, CP symmetry had promised that heads and tails were equally likely, that particles and antiparticles should emerge and decay with identical probabilities. Cronin and Fitch discovered that the coin was loaded ever so slightly favouring one outcome over the other. The imagery helps to ground this strangeness. Picture two dancers performing a routine that is supposed to be perfectly mirrored. Each step, each spin, each gesture should match. But in practice, one dancer tilts their head a little more, lingers a little longer in one move, and the routine is no longer symmetric. It still looks graceful, but the difference is there, unmistakable to anyone watching carefully. The kaons were performing just such a routine, their decay patterns revealing that the mirror and swap operation did not bring the dance back to perfection. For the first time, physics had direct experimental proof that matter and antimatter do not behave identically. And that single crack in symmetry opened up profound implications. After all, one of the great mysteries of cosmology is why the universe is filled with matter at all. If matter and antimatter had been produced in perfect balance during the Big Bang, they should have annihilated each other, leaving only radiation behind. There should be no stars, no planets, no people, just light. But here we are. Something tilted the scales, allowing a tiny excess of matter to survive. The CP violation seen in kaons may be one piece of that puzzle. Perhaps in the furnace of the early universe, these subtle imbalances added up, giving matter a slight edge. Even a difference of 1 part in a billion would be enough to leave behind the matter that now fills galaxies. Though the effect observed in kaons is not large enough on its own to explain the cosmic imbalance, it proved that the principle was possible. that the laws of physics themselves carry within them a preference, however faint. For their discovery, Cronin and Fitch received the Nobel Prize in 1980, recognition that this quiet imbalance was one of the most profound clues about why we exist. The neutral kaons, living for less than a fraction of a blink, had held within their decays the story of survival. Without their whisper of asymmetry, perhaps nothing solid would remain. There is a deep comfort in thinking of it this way. The existence of everything you see, the trees outside your window, the stars in the sky, the glow of your own reflection, is tied to a preference hidden in the laws of physics. Nature is not perfectly impartial. It bends just slightly toward matter. It is as though the cosmos, in the earliest moments, made a quiet choice, favouring substance over its perfect twin. That choice, imperceptible to all but the most sensitive experiments, is the reason we can ask these questions at all. And yet, the story does not end here. If CP symmetry can fail, what does that mean for the other discrete symmetries of physics? What about charge, parity, and time reversal when considered together? Is there some deeper anchor that holds even when individual balances tip? The next step in our journey is to explore the strange alphabet of C, P, and T, and the reassurance that even when parts of the ledger tilt, the whole remains level. The discoveries of Wu, Cronin, and Fitch had left physicists in a strange position. Symmetry, once treated as a sacred foundation, was now visibly cracked. The mirror could lie, as Wu had shown, and even when you combined a mirror flip with a swap of matter for antimatter, the dance still came out uneven, as Cronin and Fitch revealed with their kaons. But could there still be a deeper principle that held true, something unshakable beneath the layers of broken balance? To answer that question, physicists turn to the alphabet of discrete symmetries, C, P, and T. C stands for charge conjugation, the rule that swaps particles with their antiparticles. In this operation, an electron becomes a positron, a proton becomes an antiproton, and so on. If the laws of physics were perfectly symmetric under C, then the universe would be blind to whether it was filled with matter or antimatter. A movie of particle interactions would look the same no matter which version you played. P, as we've already seen, is parity, the mirror reflection. Imagine flipping the world as if it were written backward, left and right exchanged, like reading in a mirror. If parity symmetry held universally, then every process could happen just as easily in its mirror twin. Wu's experiment, of course, showed us that parity is not absolute. The weak force refuses to follow that script, choosing left over right without apology. T stands for time reversal. This one is perhaps the most haunting of the three. Imagine a film of a glass falling and shattering on the floor. Run it backward, and the shards leap up and reassemble. The glass returns to the table. Time reversal symmetry would mean that the microscopic laws work identically in both directions. At the level of the fundamental equations, it often seems that they do. But when we confront the actual behaviour of certain particles, we find that the arrow of time has a preferred direction. On their own, each of these symmetries has shown cracks. C is not absolute, since we know matter and antimatter can behave differently. P is not absolute, thanks to Wu's cobalt-60 experiment, and CP together is not absolute, as Cronin and Fitch proved. That leaves us with the unsettling possibility that maybe T is not absolute either, that time itself might not be entirely reversible in every corner of physics. But then comes the reassurance. Although each of these rules can fail individually or in pairs, the combination of all three, CPT taken together, appears to be inviolable. This is called the CPT theorem, and it is one of the most profound principles of quantum field theory. It tells us that if you take any physical process and you swap particles with antiparticles, reflect the world in a mirror, and then run the film backward in time, the universe cannot tell the difference. No experiment has ever contradicted this. It is the unbreakable anchor. The imagery here is comforting. Imagine a balance beam scale with two pans that can tilt up or down. If you only watch one pan, you might see it sink lower than the other, and you might worry that balance has been lost. But when you step back and see the entire beam, you notice that the bar itself is still level, that the system as a whole is in equilibrium even though the pieces have shifted. That is CPT symmetry. Left and right may not be equal. Matter and antimatter may not behave the same. The arrow of time may lean forward, but when all three operations are combined, the universe maintains its underlying fairness. This discovery provided a sense of grounding in the midst of broken rules. Physicists could accept parity violation, CP violation, even potential time asymmetry, because they had this assurance. The grand ledger still balanced when written in the language of CPT. Like a cosmic accountant, the universe may allow small irregularities in the columns, but when the full page is tallied, the sum comes out exact. There is also something quietly poetic in this. The idea that only when we consider everything together, particles and antiparticles space-flipped, time reversed, do we see the true symmetry of nature. It is a reminder that partial views can mislead us, but the whole reveals a deeper order. Life often feels the same. Seen in fragments, things appear chaotic, unfair, asymmetric. But when you step back far enough, sometimes you glimpse a larger balance, not in every detail, but in the structure of the whole. CPT symmetry is not just abstract theory. It guides the construction of modern physics. When scientists design experiments to test the standard model, they do so knowing that CPT invariance is a requirement. If it were ever broken, the very foundations of our theories would collapse, and we would need to rewrite physics from the ground up. So far, CPT has never failed. In a universe where so many assumptions have crumbled, this steadfastness feels like a quiet reassurance, a steady heartbeat beneath the noise. You might imagine it like a cosmic compass, one that always points true even when local maps are misleading. Or like a great metronome that keeps perfect time, ensuring the music of physics does not fall into chaos even when individual instruments falter. The comfort comes from knowing that there is a rule too deep to be broken, a symmetry too fundamental to be bent. And yet, this is not the end of the story. Because while CPT assures us of balance, the violations of CP and CP continue to matter. They are the cracks through which reality as we know it emerges. Without them, matter and antimatter would have annihilated into nothing but light, leaving behind no atoms, no stars, no people. Symmetry may provide stability, but it is asymmetry that provides existence. The beam stays level, but the pans must tip for us to be here. So we leave this session with a paradoxical comfort. The universe is both broken and whole, asymmetric and balanced, tilted and level. In that tension lies the story of everything that exists. And as we continue, we will follow that story into the early universe itself, where symmetry is shattered in fiery transitions, where forces split apart from a once unified field, and where the very rules of reality crystallized into the structure we now inhabit. Imagine the earliest moments of the universe, a time so hot and dense that words like plasma or furnace are far too tame. In that unimaginable heat, the familiar forces that guide our world today were not separate, not distinct. Gravity, electromagnetism, the strong force that binds atomic nuclei, and the weak force that governs radioactive decay. These were not yet individual threads. They were braided together in a single, unified rope, a symmetry so perfect and so simple that it left no room for the fractures we know now. This idea is sometimes called grand unification, and though we cannot reproduce those energies in any laboratory, the mathematics of particle physics suggests it. At sufficiently high energies, the strengths of the different forces begin to converge as though they are remembering that they were once one. The electroweak force, which we know from particle accelerators, is the first example. Electromagnetism and the weak force, now so different, were once indistinguishable. Push to higher energies still, and perhaps the strong nuclear force joins them. Push further yet, and maybe gravity, elusive and stubborn, folds into the union as well. The picture is incomplete, but the suggestion is clear. Unity lies in the past, fragmentation in the present. To picture this, it helps to imagine a pane of stained glass. At first, when unlit, it is only a sheet, uniform and whole. But when sunlight pours through, the hidden divisions reveal themselves, reds, blues, and golds shining in different panels. The glass was always one, yet within it lay the seeds of multiplicity. In the universe, the initial oneness of the forces was broken as the cosmos cooled, and what had been uniform fractured into pieces, each taking on its own role. Cooling in this story is not merely the lowering of temperature as we experience when ice cubes form in a freezer. It is the relaxation of unimaginable energies, the slowing of frantic quivering into something calmer, and with cooling comes phase transitions. Just as water can freeze into ice or boil into steam, the fields of physics undergo transitions. One symmetry after another breaks, and with each break the rules of nature shift. At first glance, the word breaking sounds destructive, but here it is creative. From the breaking of symmetries comes diversity, and from diversity comes the possibility of structure. If all forces had remained unified forever, the universe would be too bland, too featureless to host complexity. By losing perfection, it gained richness. It is like a choir beginning with one note and then branching into harmony, voices splitting into soprano, alto, tenor, and bass. The song is no longer pure and uniform, but in the branching it becomes beautiful. When the electroweak force separated into electromagnetism and the weak force, the consequences were profound. Electromagnetism became the gentle sculptor of atoms, binding electrons to protons, lighting stars, and carrying our radio signals and lamp glow. The weak force, quieter but no less vital, orchestrated nuclear reactions, beta decays, and the processes that fuel the sun's heart. Without that split, the stars could not burn as they do, nor could the elements of life have formed. The breaking, paradoxically, was an act of creation. The strong nuclear force, meanwhile, ensured that protons and neutrons clung together within atomic nuclei. Without its separation and distinct identity, matter itself would have remained a soup of quarks, never settling into the stable particles that anchor our world. And gravity, though perhaps the most stubborn to unify with the others, settled into its long, patient role, shaping galaxies and worlds through attraction alone. To carry the metaphor further, think of a potter's clay wheel. At the start, the clay is an indistinguishable lump, shapeless and uniform. As the wheel spins and the potter's hands press, ridges and curves form. The clay loses its formless unity, but in doing so becomes a vessel that can hold water, wine, or bread. The breaking of symmetry in the universe was the potter's touch, sculpting a cosmos where stars could shine, planets could form, and life could take root. Yet the memory of unity is still present. Physicists trace the running strengths of the forces as they vary with energy, and in their graphs, the lines converge, almost touching at energies far beyond our reach. It is like hearing the faint echo of a single note hidden behind a chorus, a reminder that before the splitting, there was one voice. And so, the story of the early universe is not only a story of explosions and expansion, but of cooling and breaking. Each fracture of symmetry gave the universe new structure, new possibility. The stained glass pane cracked into many colours, and the sunlight that passed through illuminated galaxies, atoms, and you, sitting here listening. It can feel strange to think that imperfection is what allowed existence, but that is the quiet lesson of symmetry breaking. The flawless does not sustain. It is the fractured that endures. A cosmos with one force might have been tidy, but it would also have been lifeless. The world we inhabit is the result of cracks spreading through an early perfection, a perfection that could not last and perhaps should not have. As we move forward, we will see that these fractures were not always clean. Some came with drama, sudden and sharp, like a pane of glass shattering. Others came quietly, softly, like fog rolling in, almost imperceptible. And some carried within them not only beauty but puzzles that remind us that our existence is still perched on mysteries unresolved. But before we reach those, we must pass through one of the most astonishing episodes of all, the moment when the universe, already fractured, suddenly swelled in an expansion so violent and so brief that it defies imagination. This is the story of cosmic inflation, the smoothing of rough edges, the stretching of the very fabric of space, and the quiet reheating that followed. The early universe, as it fractured from unity into many forces, was not only cooling but also facing puzzles of scale and smoothness. Astronomers, looking across the sky at the glow of the cosmic microwave background, discovered that regions of space separated by billions of light years are astonishingly similar in temperature, as if they had once been in contact. Yet according to the old, pre-inflationary models, those regions should never have touched. Light itself would not have had time to cross the gap between them in the age of the universe. This was called the horizon problem. How could distant patches of sky agree on a temperature if they had never exchanged a word of thermal gossip? Then there was the flatness problem. Measurements of space reveal that the geometry of the universe is eerily close to flat, like a sheet of paper, rather than sharply curved like a sphere or dramatically open like a saddle. But to achieve such flatness naturally, the initial conditions of the cosmos would have had to be tuned with almost impossible precision, like balancing a pencil on its tip so perfectly that it never falls. Why should the universe be so delicately poised? Finally, there was the issue of relics. Theories predicted the existence of exotic particles, such as magnetic monopoles, objects that would carry a single magnetic pole, north without south or south without north. These would have been copiously produced in the seething high-energy soup of the early universe, yet astronomers found none in the sky. Where had they gone? In 1980, a young physicist named Alan Guth proposed an audacious solution: inflation. For a tiny fraction of a second, far shorter than any heartbeat or blink, the universe expanded exponentially, swelling by a factor beyond comprehension. During this burst, distances doubled, and doubled again, and doubled again, so rapidly that irregularities were ironed out. Like stretching a crumpled sheet until it appears smooth, inflation could make the universe look uniform across vast distances. Regions that once sat close enough to exchange information were flung apart, carrying with them the matching temperatures we still see today. Inflation also explained flatness. Imagine inflating a balloon until its surface appears almost flat to someone standing on it. By stretching space to cosmic scales, inflation made any curvature negligible, leaving us with a universe that looks flat even if it began with curves. What seemed impossibly fine-tuned could emerge naturally from this runaway growth. And as for relics like monopoles, inflation provided a way to dilute them. Just as dust on a balloon becomes almost invisible when the balloon is blown up, so the density of relic particles would drop as space expanded, leaving them vanishingly rare. The absence of monopoles in the night sky ceased to be a puzzle and became an expected outcome. Yet inflation is not only about stretching, it is also about what comes after. The universe during inflation was dominated by the energy of a hypothetical field, the inflaton. This field drove the rapid expansion, but when inflation ended, that energy was released. The inflaton decayed, pouring its stored energy back into the universe in the form of particles and radiation. This process is called reheating, and it is how the cosmos once again filled with the ingredients needed for stars and galaxies. The image here is almost domestic. A kettle of water set on the stove, boiling until steam fills the room, carrying warmth and motion everywhere. Inflation was the boiling, the furious growth of bubbles and vapour. Reheating was the steam condensing, filling the kitchen again with heat, making it a place where bread can rise and tea can be poured. Without reheating, the universe would have remained an empty, frozen expanse. Instead, it became vibrant, crowded with particles, busy with energy. The beauty of inflation lies in its dual character. On one hand, it is an extreme idea, a proposal that space itself can swell faster than the speed of light, doubling again and again in less than a breath. On the other hand, it explains mysteries with remarkable simplicity, smoothing wrinkles, diluting relics, and setting the stage for the familiar expansion that continues even now. And inflation carries another gift. It provides the seeds of structure. Tiny quantum fluctuations, once smaller than atoms, were stretched by inflation to cosmic scales. Those ripples became the variations in density that gravity later amplified into galaxies, clusters, and the vast web of cosmic structure. Imagine the faint shimmer of heat on pavement in summer, small and random. Stretch that shimmer across the sky, and you have the blueprint for everything you see when you look up on a clear night. The evidence for inflation is indirect but persuasive. The uniformity of the cosmic microwave background, the flatness of space, the absence of relics, all fit neatly within its framework. Future experiments may yet detect the faint signature of primordial gravitational waves, tiny ripples in a space-time that inflation should have produced. If found, they would be the echo of that violent swelling, a whisper from the first fraction of a second. Of course, inflation is not the final word. Like many great ideas in physics, it opens as many questions as it closes. What was the inflaton? Why did it decay the way it did? Could inflation happen again in other regions, spawning not just one universe but a multitude, each with its own properties? These are speculations that drift near the edge of sleep, where science blends into dream. For now, it is enough to imagine the cosmos as a balloon swelling in silence, stretching smooth, then filling with warmth and light. Enough to see that the quiet tea in your cup, the warmth of your breath, the stars wheeling above, all trace back to that moment of sudden expansion and gentle reheating. Inflation was the stage setting, the preparation of the cosmic room. What followed were transitions more subtle, more like whispers than shouts, but no less crucial. Some changes came softly, not with a bang but with a fog. These are the phase transitions of the early universe, and they tell us why the story of matter's survival remains unfinished. When we think of change in nature, it is tempting to imagine it as sudden, dramatic, unmistakable. A glass shatters and the quiet room is filled with noise. Water boils, and a calm surface erupts into steam. Lightning strikes, and the sky's balance is instantly overturned. We often imagine the universe itself undergoing such transformations, one moment uniform and still, the next reshaped in fire. Yet the truth is gentler, more ambiguous. Not all transitions in the early universe were abrupt. Some came like fog instead of thunder, as soft crossovers rather than sharp breaks. To picture this, think of water cooling in autumn air. At a certain temperature, it may crystallize into ice, with sharp edges and definite structure. But sometimes it hovers near freezing, not solidifying in any clear instant. Mist rises, frost glimmers, droplets hang suspended. The transition is not dramatic but blurred, a slow passing from one state into another. So too with the fields of physics. Two major transitions in the early universe, the electroweak and the quantum chromodynamics (QCD) transitions, may not have been clean first-order phase transitions like water snapping into ice. Instead, according to the standard model of particle physics, they were smooth crossovers. Fields that once behaved symmetrically did not suddenly fracture, but gradually shifted, their roles and strengths evolving without the fireworks one might expect. The electroweak transition, in particular, holds a special place in this story. At higher energies, electromagnetism and the weak force are fused, indistinguishable partners. As the universe cooled, the Higgs field grew into its role, breaking the symmetry and giving particles their masses. Yet if this process was a soft crossover, as the Standard Model suggests, then it unfolded like morning mist, quiet and continuous, with no dramatic imbalance created between matter and antimatter. For the survival of matter, this is a problem. You see, to explain why matter outlived antimatter, the cosmos needed a way to tip the scales, just slightly, but decisively. Theorists hoped that violent first-order transitions might do this, creating bubbles of broken symmetry expanding into regions of unbroken symmetry, surfaces where conditions could favour matter over antimatter. The imagery is vivid. Bubbles colliding, fronts sweeping across the young universe, like boiling water erupting into rolling bubbles. But if instead the transition was a soft blur, then the conditions for such imbalance never arose. Matter and antimatter would remain nearly perfect twins, destined to annihilate, leaving behind a cosmos of empty light. The QCD transition, tied to the strong nuclear force and the binding of quarks into protons and neutrons, offers a similar puzzle. It too appears to be a smooth crossover, not a sharp break. Like fog forming instead of a sudden freeze, it reshaped the landscape without leaving the kind of dramatic imbalance that baryogenesis, the birth of matter, seems to require. This leaves us with a quiet paradox. The Standard Model of particle physics, so successful in describing experiments, predicts transitions that are too gentle to explain why we are here. They are beautiful in their subtlety, but insufficient in their consequences. We are left with the sense that something more must lurk beyond the Standard Model, some new physics that sharpens the edges or tilts the balance. The imagery here is haunting. Imagine waiting for a storm to break, only to feel the drizzle fade into mist. The sky never cracks, never shouts, it only sighs. That sigh may be beautiful, but it does not strike the imbalance needed for existence. In a sense, we live in a universe where the official story whispers too softly. The Standard Model alone does not give us the shout that made matter win. And so physicists search for what could sharpen the fog. Supersymmetry, extra Higgs particles, hidden dimensions, all have been suggested as ways to turn soft crossovers into decisive transitions. Perhaps in those added layers, the universe gained the small push it needed. Perhaps the whisper was amplified into a murmur strong enough to favour matter by just 1 part in a billion. To the listener drifting towards sleep, there is something strangely comforting in this uncertainty. It reminds us that not all puzzles are solved, that even in the cosmic past there remain silences we cannot fill. The survival of matter depends on a gap in our knowledge, a place where physics has yet to show its hand. The fog has not lifted entirely, and perhaps that is fitting. For the story of existence, like the story of a quiet evening, does not always come with thunderclaps. Sometimes it drifts forward gently, with transitions that are barely noticed, until you look back and realise how much has changed. The early universe's fog-like transitions are part of that tale. They remind us that not all creation is violent. Some of it is soft, understated, the kind of change you only feel when you realise the world around you has subtly shifted. As we step forward, we will leave behind the softness of these transitions and face the question more directly. How did matter survive at all? If the Standard Model alone cannot answer, then we must look to baryogenesis, the strange processes that favoured matter over antimatter. It is a problem still unresolved, a cosmic riddle at the heart of why you are here to listen tonight. In 1967, a Soviet physicist named Andrei Sakharov sat with a question that was as simple as it was staggering. Why does anything exist at all? If the laws of physics treat matter and antimatter as twins, then the early universe should have produced them in equal numbers. They would have met, embraced and annihilated each other in a blaze of radiation, leaving behind a universe filled with light but no substance, no atoms, no stars, and certainly no people. Yet here you are, and here I am, proof that somehow matter won. Sakharov realized that for matter to emerge from that initial symmetry, 3 unlikely conditions had to be met. Think of them as 3 locks on a heavy cosmic door. Only if all 3 turn together can the door swing open to let matter slip through. Miss even one, and the door stays shut. The first lock is called baryon number violation. In ordinary life, the number of protons and neutrons, the baryons, seems fixed. They can rearrange, fuse in stars, or decay under rare conditions, but they do not usually appear from nothing or vanish into thin air. Yet to tip the balance between matter and antimatter, the universe must have allowed the creation or destruction of baryons themselves. The rulebook must have included a line saying, "Under certain conditions, the tally of matter may change." Imagine an accountant's ledger where, occasionally, the rules permit the addition or removal of entries without an opposite adjustment. Without that flexibility, no imbalance could ever form. The second lock is CP violation, where C stands for charge conjugation, swapping matter for antimatter, and P stands for parity, flipping space like a mirror image. If the laws of physics respected CP symmetry perfectly, then matter and antimatter would be exact reflections, always behaving as mirror twins. But to favour matter, nature must lean slightly to one side, breaking the mirror. Experiments have shown this to be true. In weak nuclear interactions, the mirror does not hold. The universe favours left-handedness. Neutrinos, for instance, spin only one way. It is as if the cosmic dice are loaded, not enough to overturn every game, but enough that over time the odds begin to shift. The third lock is departure from equilibrium. Balance, by its very nature, preserves symmetry. To create an imbalance, the universe must have been pushed out of balance into a place where the usual cancelling did not occur. Picture a teeter-totter with 2 children evenly balanced. Only if one jumps off, or if the plank is shaken, can the balance be broken. In cosmology, this shaking came from the rapid expansion, cooling, and phase transitions of the young universe. In those brief, unsettled moments, the conditions existed for matter to slip through: baryon number violation, CP violation, and disequilibrium. 3 locks, 3 requirements. Together they form the Sakharov conditions, a simple yet profound framework that explains what must be true if matter is to survive. Each is necessary, none alone is sufficient. If you had baryon number violation but no CP violation, matter and antimatter would still balance perfectly. If you had CP violation but no disequilibrium, the imbalance would wash away like ripples in a calm pond. All 3 had to act in concert, a trio of cosmic conspirators opening the way for our existence. The imagery is not of a grand explosion or a decisive battle, but of a door quietly swinging on its hinges. Behind that door lies the possibility of galaxies and life. Without it, the universe would have been a brilliant but empty sea of radiation. It is humbling to think that your breath, your heartbeat, the very atoms in your bones all depend on these 3 conditions having been satisfied in a universe younger than a blink. Sakharov's insight was both technical and poetic. In the stark language of particle physics, he wrote down the equations. But in spirit, what he described was the delicate unlocking of possibility. Each condition is like a key turning, and together they open the hidden passage that led to us. The challenge, however, is that while we know these conditions in principle, in practice the physics we've observed does not seem strong enough. We have glimpsed baryon number violation in theoretical models, but not yet in experiments. We have measured CP violation in kaons and B mesons, but it appears too weak. And while the universe certainly fell out of equilibrium in its early expansion, the known transitions may have been too gentle. The locks exist, but the keys we have do not seem to fit them well enough. That is where the mystery deepens, and where the story carries us forward. The door has opened. We know this because matter survived. But we cannot yet see the full mechanism. Somewhere, perhaps in physics beyond the standard model, lie the missing turns of the key. Supersymmetry, hidden fields, or particles we have not yet found may provide them. Or perhaps the solution lies in processes we cannot yet imagine, hidden in the fabric of space itself. For now, Sakharov's three conditions remain our compass, pointing us to what must have happened even if we do not yet know how. They are the silent rules that shaped survival, the locks that allowed one particle of matter in a billion to escape annihilation. They remind us that existence is not inevitable. It is conditional, contingent, the outcome of rules that could have turned another way. As you let these thoughts drift, you might imagine three doors in a hallway, each heavy and silent. You approach, carrying the weight of the cosmos on your shoulders. Only if all three open can you step through into a world of stars and seas. The doors creak one by one until at last there is a passage. You step through, and here you are. The standard model of particle physics is often described as one of humanity's greatest achievements, a framework that has predicted experiment after experiment with almost eerie accuracy. It tells us how quarks assemble into protons and neutrons, how electrons dance around nuclei, how forces are carried by photons, gluons, and W and Z bosons. It is like a finely tuned orchestra score, each instrument carefully noted, each harmony well rehearsed. Yet when it comes to the matter-antimatter mystery, this otherwise flawless symphony falters. The notes exist, but the melody is too faint. Think again of Sakharov's three doors. The standard model in principle does offer keys to turn them. There are processes that could change barrier number, subtle effects of quantum fields that allow the universe to blur what seems forbidden. There is CP violation, discovered in the decays of kaons and B mesons, a quiet but real asymmetry between matter and antimatter, and the young universe was certainly out of equilibrium during its expansion and cooling. At first glance, it seems the model ticks all three boxes. The lock should open, the door should swing, but the trouble lies in the details. The CP violation encoded in the standard model comes from what is known as the CKM matrix, a mathematical table that describes how quarks change flavor through weak interactions. Buried in this matrix is a complex phase, a subtle twist that allows particles and antiparticles to behave differently. This is the flicker of bias nature needs, yet the numbers tell us it is far too weak. It is like striking a match and expecting it to light a bonfire. The flame exists, yes, but it is swallowed by the dark long before it can ignite anything larger. The electroweak transition too is a disappointment. For the standard model, this symmetry breaking is not the violent bubble nucleating, wall colliding drama that could have pushed the cosmos into strong imbalance. Instead, it is a smooth crossover, a gentle shift like mist condensing rather than ice cracking. Without that turbulence, the out-of-equilibrium conditions remain too mild to generate the imbalance Sakharov's recipe demands. The kettle never truly boils, it only simmers. When we calculate what the standard model predicts, we find a gulf between theory and observation. The universe we observe has a baryon-to-photon ratio of roughly 6 parts in 10 billion, or Eta approximately 6 times 10 to the negative 10th power. That tiny fraction was enough to see galaxies and life, but it is still orders of magnitude larger than the imbalance the standard model can explain. By its math, the candle never catches, the simmer never boils, and the matter that should have survived amounts to far less than what we see. Physicists sometimes describe this failure with frustration but also with awe. It is humbling to realise that the theory which predicts the Higgs boson to remarkable precision cannot explain why you exist to hear about it. The Standard Model is a palace with intricately carved walls, precise and consistent, yet in the foundation there is a missing stone. Everything rests upon it, yet it is absent. Imagery can help. Picture yourself holding a balance scale with matter on one side and antimatter on the other. According to the Standard Model, the scale should be tilted by the weight of a feather, just enough to mark that symmetry has been broken. But to match the universe we see, the scale must be tilted by a stone. A feather is not enough. A feather cannot explain stars or oceans or the curve of your own hand. Some have compared the Standard Model's insufficiency to a child's toy hammer. It has the shape of a tool, and it can make a tap, but it cannot split wood or break stone. The principle exists, but the strength does not. Nature needed a hammer of steel, yet the Standard Model offers only plastic. This shortfall is not a failure of science, but an invitation. It tells us there is physics yet to be discovered. Perhaps new particles, undiscovered cousins of the ones we know, play their role. Perhaps multiple Higgs fields exist, reshaping the electro-weak transition into something sharper and more violent. Perhaps supersymmetry lurks just beyond our reach, amplifying CP violation into something fierce enough to matter. Or perhaps the answer lies not in particles at all, but in entirely new dynamics of space-time. For now, what is clear is that the Standard Model, magnificent though it is, cannot be the whole story. It carries us far but leaves us at the doorstep, staring at a door still locked. The candle flickers. The feather shifts the balance. The toy hammer taps against stone. It is not enough. There is a quiet humility in admitting this. It is a reminder that physics is not complete, that the cosmos still guards secrets. When you look up at the stars tonight, you see not just what is explained, but what remains unexplained. Each galaxy is a testament to that unsolved puzzle, why matter survived when it should not have. And so the journey continues. We know what is missing, even if we do not yet know what fills the gap. In the next step, we will reflect on just how thin the margin was, how fragile the imbalance turned out to be. For every billion particles, one survived. 1 in a billion, and that was enough to fill the sky with stars and the earth with oceans. The numbers are so vast that they almost slip through thought like water, through fingers, but let us try to hold them gently. In the beginning, when the universe was new, for every billion particles of matter there was a billion particles of antimatter. They rushed toward each other in the expanding fire, paired off, and in blinding flashes they annihilated. The glow from that immense destruction still lingers today, stretched into the faint microwave background that hums across the sky. Yet when the dust settled, if one can even use that word for such a primordial chaos, one matter particle out of every billion had no partner. A solitary survivor in a crowd that otherwise vanished. That fraction, that 1 in a billion, is all of us. The galaxies wheeling through space, the stars burning in spirals, the planets, the oceans, the mountains, and the breath you are drawing at this very moment. They are all built from that sliver. If the imbalance had been perfect, if matter and antimatter had cancelled with no residue, the universe would be a pure sea of light. Beautiful in its way, perhaps, but without form, without weight, without life. Instead, a few grains of sand clung to the cosmic beach, and from them everything else was shaped. It is hard to convey just how fragile that survival was. Imagine a vast stadium filled with 1 billion people, each one paired with a twin. Suddenly, the lights dim, and in a coordinated act they vanish together, twin with twin, until only one person remains standing in the empty seats. That lone figure represents all of matter in our universe. The rest, the billion minus one, is gone. The scale of annihilation is overwhelming. Yet the quiet presence of the survivor is enough to build a cosmos. The cosmic microwave background, first discovered by Penzias and Wilson in 1965, is the fossil proof of this history. It is the stretched glow of that annihilation, cooled by expansion, until it now shines in microwaves. Every time we detect it with our instruments, we're listening to the echo of the Great Disappearance, and also to the whisper of the survivors. The density ripples mapped in that glow show us the tiny variations that grew into galaxies, but they also encode the baryon to photon ratio. They confirm that for every billion photons, there are only about 6 baryons, protons and neutrons. That ratio is the silent signature of the 1 in a billion imbalance. The fragility of it is humbling. We are accustomed to thinking of existence as inevitable, of matter as sturdy and solid. A rock feels heavy in the hand, a mountain looms immovable on the horizon, a planet circles in steady rhythm. But all of this rests on a numerical accident, on the fact that in the early fire, 1 particle in a billion escaped annihilation. If the number had been slightly different, if it had been 1 in 10 billion or 1 in 100 million, the story would have changed. Too few survivors, and the universe would be sparse, perhaps too thin to form galaxies. Too many, and the early cosmos would have collapsed under its own weight. The balance was razor thin, yet it was struck just so. Think of a whisper in a crowded hall, drowned by the noise of countless voices. For most of the hall, the whisper disappears, but in one corner it lingers, faint but present, and when the voices fade, that whisper is all that remains. Our universe is built from that whisper, or picture a last leaf clinging to a branch after autumn has stripped the tree bare. Against the odds, it holds. Winter passes, and from that remnant spring is born again. In the same way, the cosmos held on to a remnant of matter, and from it came stars, chemistry, and life. Physicists sometimes call this the baryon asymmetry problem. But such a phrase feels too clinical for the enormity of what it means. It is not just a problem, it is a miracle of survival. It is the story of how almost everything disappeared, and how the tiny remainder became everything we see. To look at the night sky is to see the survivors shining. To touch your own hand is to touch what escaped. And yet the mystery remains. We know the scale of the imbalance, but not its cause. The standard model cannot explain it. CP violation as we know it is too weak. Electro-weak transitions are too smooth. The keys we hold do not quite fit the locks. Somewhere, hidden in the unknown physics beyond our tested theories, lies the true story of how 1 particle in a billion survived. Perhaps in the behaviour of neutrinos, in subtle differences still being chased by experiments, we will find the answer. Perhaps it rests in particles not yet discovered, or in forces that once acted but now lie dormant. For the listener drifting towards sleep, the thought may carry a certain peace. Your existence is not ordinary, it is improbable. Every breath, every heartbeat, every quiet thought you carry is balanced on the knife edge of that 1 in a billion survival. You're the unlikely outcome of a cosmic coin toss, the residue left when near-perfect annihilation played out. Yet from that residue came music and mathematics, rivers and forests, sorrow and love. And so we pause, marvelling at the fragility and the fortune of it. The early universe was a stage where matter and antimatter performed a dance of mutual destruction, and almost all of it was lost in light. But the faint imbalance endured, like an ember refusing to go out. From that ember, the fire of the stars was lit, and from the stars came you. If you imagine the universe in its first split seconds as a vast simmering pot, you will not be far from the image physicists use. At temperatures trillions of degrees higher than the core of any star, particles rushed and collided in an endless boil. In that storm, all 4 of nature's forces may once have been united, not yet fractured into the familiar forms of gravity, electromagnetism, and the nuclear forces. But as the cosmos expanded and cooled, its perfection began to crack. One of the most important cracks occurred when the electroweak force, the unity of electromagnetism and the weak force, broke into two distinct rules. In the standard model, this electro-weak transition is as smooth as fog forming over a meadow at dawn. It does not happen with sudden bangs or cracks, but in a gentle drift. That softness, as we've seen, is the reason the standard model cannot explain why matter survived. For Sakharov's doors to swing wide, the universe needed something sharper, something like a true phase transition, a moment where reality boiled, where bubbles of a new order formed and expanded into the old. This is the central idea of electro-weak baryogenesis. If the electroweak symmetry breaking had been a first-order phase transition, the universe would have boiled like a pot on a stove. Imagine bubbles forming in a hot broth, their surfaces shimmering, growing, and then colliding with one another. Each bubble would represent a region of space where the electro-weak symmetry had broken. At the thin walls between these regions, strange and asymmetric physics could have taken place. Matter and antimatter might have encountered the rules differently as they crossed those walls, tipping the balance ever so slightly toward matter. Inside the bubbles, particles would gain their familiar masses through the Higgs field. Outside, they would still be massless. The boundaries were like shifting curtains, drawn and redrawn in a cosmic theatre. Across those curtains, CP-violating interactions could have nudged matter into lingering, while antimatter slipped away into annihilation. Slowly, bubble by bubble, the broth of the early universe could have simmered its way into an imbalance large enough to survive. Yet here too the standard model falters. The Higgs boson, discovered in 2012, seems too heavy for such a sharp transition. Instead of bubbles boiling, we get only the quiet fog. Electroweak baryogenesis remains a beautiful idea, but in its pure standard model form it does not work. The transition is too soft. The broth does not boil, only steams. But that does not mean the story is closed. If there are new particles, perhaps cousins to the Higgs, or partners to the ones we already know, they could reshape the transition into something sharper. Supersymmetry, extra Higgs doublets, or new scalar fields might tilt the balance. Each extension to the standard model is like adding new spices to the broth, and under the right conditions the simmer could indeed become a boil. The idea is not only theoretical, it leaves behind signals we might one day detect. When bubbles collide, they do not do so silently. They shake the fabric of space-time itself, sending ripples outward, gravitational waves. Unlike sound waves, which travel through air, or water waves, which ripple across a pond, gravitational waves stretch and squeeze the very geometry of the universe. In the case of electroweak baryogenesis, these waves would be faint, but they might still be within reach of future instruments. One such experiment is LISA, the Laser Interferometer Space Antenna, planned by the European Space Agency and NASA. Imagine 3 spacecraft floating millions of kilometers apart, connected by lasers so precise they can sense distortions smaller than the width of an atom. If bubbles really did boil and collide in the early universe, the faint hum of their violence might still be resonating through space-time. Lisa could, in principle, hear that song, a symphony from when the cosmos was less than a trillionth of a second old. The image is almost dreamlike, a cosmic broth bubbling in silence, yet somehow leaving behind a music that only space-time remembers. To us, it would be evidence that the imbalance of matter over antimatter was not an accident, but the outcome of a great boiling, a brief but decisive imbalance written in the very birth of forces themselves. It is worth pausing to reflect on how extraordinary this is. Our daily lives are surrounded by transitions. Water boils, ice melts, bread rises in the oven, mist condenses on a window pane. but those familiar changes are echoes of the same principle. Order shifting into a new form. To think that the universe itself once boiled in this way, and that those bubbles may have tipped the balance that allows us to exist, is both humbling and strangely comforting. It ties the great cosmic history to the simple kettle on your stove. Both follow the same hidden rules. The challenge, of course, is that so far experiments have not confirmed the sharp transition electroweak baryogenesis requires. The standard model Higgs, with its measured mass of 125 GeV, is too heavy to make the broth boil. It leaves us with fog, not bubbles. That gap is one of the many reasons physicists search for physics beyond the standard model. Somewhere out there might be a clue, a new field, or a new symmetry waiting to be broken in just the right way. For now, electroweak baryogenesis remains an elegant possibility, a theory that sits just beyond our reach. It paints the early universe as a pot bubbling with hidden structure, with bubbles forming and bursting, each collision leaving behind a tiny tilt toward matter. It suggests that if we listen carefully enough, through instruments like LISA, we might one day hear the faint tremors of that boiling, like bells ringing from a time when space itself was still new. If electroweak baryogenesis is like the image of a bubbling pot, then leptogenesis is more like a story of seeds. Tiny, almost invisible seeds carried quietly in the wind, landing on soil they were never meant to reach, yet somehow growing into the trees that now fill the forest. To understand leptogenesis is to understand how some of the faintest, ghostliest particles in the universe may have shaped everything we see. The neutrino has always been a kind of shadowy figure in physics. Proposed by Wolfgang Pauli in 1930 as a desperate act of bookkeeping to explain missing energy and beta decay, it went undetected for decades. Even now, though trillions pass through your body every second, you will never notice them. They hardly interact with matter. They slip through walls, through the earth, through the sun. They are particles that behave like whispers in a crowded room, present but almost impossible to hear. But there may have been a time when neutrinos were not quite so shy. Imagine the universe just after inflation, reheated and dense with possibilities. Among the zoo of particles were perhaps very heavy cousins of today's neutrinos, particles with masses far beyond anything we could create in colliders. These hypothetical giants are called Majorana neutrinos, after the Italian physicist Ettore Majorana, who imagined that some particles could be their own antiparticles. If these heavy Majorana neutrinos existed, their decays could have been asymmetric. That is, they might have decayed slightly more often into leptons than into antileptons. Such a small tilt may sound insignificant, but remember our theme. The universe is built upon 1 in a billion imbalances. The lepton excess could then be converted into a baryon excess through a rare but important kind of transition known as a sphaleron. The word sounds exotic, but the concept can be approached gently. A sphaleron is a non-perturbative solution in the electroweak theory, a way of tunneling through energy barriers between different field configurations. Imagine rolling hills separating valleys, with a ball that normally stays in its own valley. A sphaleron is like a gust of wind strong enough to push the ball up and over into another valley. In the universe, sphalerons connect lepton number to baryon number. They allow an imbalance in leptons to be reshaped into an imbalance in baryons, into matter itself. So in leptogenesis, neutrinos act as the secret planters of asymmetry. They sowed the imbalance first in the lepton fields, and sphalerons later converted those seeds into the matter that built the stars. The image is almost pastoral, a field waiting for harvest, invisible seeds scattered, and in time, an entire universe blooming from them. One of the elegant features of this idea is that it ties together two mysteries at once. First, it could explain why matter survived over antimatter. Second, it could explain why neutrinos today are not massless, as the original standard model predicted, but instead carry tiny masses. We know from neutrino oscillations the way neutrinos change flavour as they travel, that they must have mass, but that mass is astonishingly small. The seesaw mechanism, a favourite among theorists, explains this by proposing that light neutrinos we observe are balanced against the immense mass of their heavy ancestors. The heavy ones gave the light ones their tininess, as if by leaning on a seesaw and lifting their smaller cousins high into the air. Here again, the everyday image is helpful. Think of an old seesaw on a playground. On one side sits a giant, hardly moving at all. On the other side sits a child, lifted almost to the sky by the giant's weight. The child rises because the giant presses down. In physics, the giant is the heavy Majorana neutrino, and the child is the light neutrino we measure today. Their relationship explains the smallness of neutrino mass, and potentially the imbalance that gave us matter. Experiments now search for traces of this hidden story. One key test is neutrino-less double beta decay, a rare nuclear process that would only happen if neutrinos are indeed Majorana particles, that is, their own antiparticles. Detecting it would be like finding a footprint in soft earth, a quiet but undeniable sign that the neutrino carries this hidden dual identity. Around the world, enormous detectors wait in silence, buried under mountains or immersed in liquid noble gases, listening for these almost imperceptible events. So far, silence continues, but the search itself is a song of patience. The beauty of leptogenesis lies in its simplicity. It suggests that the quietest particle, the one that hardly interacts at all, may have been the decisive actor in the grand cosmic drama. The neutrino, a particle that does not light the stars or shape the atoms, may nonetheless be the hidden author of galaxies. The seeds it scattered in the early universe might have grown into everything we know. It is worth letting that thought settle as you drift deeper into quiet. The universe we see is vast, yet its fate may have hinged on a particle so elusive that billions pass through your pillow each night as you sleep. They leave no mark, no warmth, no sound. And yet, long ago, their ancestors may have whispered just loudly enough to tip the balance of existence. If you have ever held a pearl and turned it slowly under the light, you know the feeling of searching for hidden flaws. To the eye, it may appear perfect, smooth as glass. Yet when you tilt it, you sometimes find a tiny dimple, a hidden curve, an imperfection that tells you this object was once alive, once grown, once touched by time. Modern particle physics often feels like that. The slow turning of the universe's pearls under the sharpest light we can shine, searching for the faintest irregularity that might betray a deeper truth. One of the most delicate of these searches is the quest for the electric dipole moment, or EDM, of the electron. At first, the concept may sound abstract, but the idea can be softened. An EDM would mean that the electron, usually pictured as a perfect sphere of charge, is in fact slightly lopsided. Imagine an orange that is not perfectly round, but just a little stretched, with more pulp on one side than the other. For an electron, such a distortion would indicate that its charge distribution has a preferred direction, like a tiny arrow always pointing somewhere. Why would this matter? Because such a preference would break a hidden symmetry. The laws of physics, if they perfectly treated matter and antimatter alike, would leave the electron perfectly round. But if the electron carries an EDM, however faint, it would whisper that matter and antimatter are not treated equally. It would be a new crack in the mirror, another clue that CP violation hides in places we have not yet looked. The search for this tiny tilt has become one of the most precise measurements in all of science. The ACME collaboration, based in the United States, is famous for pushing the sensitivity of EDM experiments to extraordinary levels. Instead of trying to weigh mountains or smash atoms at nearly the speed of light, these scientists work in quiet rooms, cooling molecules to near absolute zero, trapping them in fields and measuring their behaviour with exquisite care. Their detectors are not roaring colliders but instruments of silence capable of hearing the faintest whisper In 2014, the ACME team reported that if the electron had an EDM, it was smaller than 1 part in 10 to the 29th centimetres. To put that scale into perspective, it is like looking for a bump on the Earth's surface smaller than the thickness of a human hair. In 2018, they improved their sensitivity by another order of magnitude, and still they found nothing. In 2023, a new experiment led by Jacob Roussy extended the search further. Again, the result was silence. No tilt, no dimple, no imperfection. Yet this silence is not empty. Each null result rules out entire families of theories. Each whisper not heard is still a sentence spoken by the cosmos, telling us where the truth does not lie. It narrows the possibilities, tightening the web of reality. A child looking at a pearl may say, "It looks perfect," but a jeweler can tell you what kinds of flaws it cannot possibly have. In the same way, EDM experiments tell us what kinds of hidden physics cannot be shaping the electron. And so the experiments continue. There is something meditative about it, the quiet patience of repeating measurements over years, waiting for a deviation that may never appear. It is like listening at night for a faint sound in the distance, unsure if it is real or imagined, but knowing that even the silence is a message. The pearl turned again and again still shows no flaw, and yet the act of turning teaches us something. What makes this search especially poignant is that if a non-zero electron EDM were discovered, it would be a revolutionary event. It would mean that CP violation is hiding not only in the rare decays of kaons and B mesons, but in the very building blocks of matter itself. It would point beyond the standard model with undeniable clarity, like finding a dimple so deep that the pearl itself could no longer be called smooth. For now, we are left in that in-between space, hope stretched across silence. The absence of discovery does not dull the search. If anything, it sharpens it. It reminds us that the hidden rules may be subtler than we imagined, written in finer print, etched into the grain of the cosmos with lines too thin to see without infinite patience. It is fitting that this part of the story unfolds so gently, with experiments designed not to smash or break, but to listen. While colliders roar with energy and smash particles into showers of fragments, EDM experiments are more like deep meditation. They wait, they breathe, they measure, they hold still, they listen for the tilt. And if one day that tilt is found, if the pearl reveals its dimple, it will be a discovery that reshapes our understanding of why matter won. For now, though, we let the silence speak, and we carry forward the patience that science so often demands. For much of this story, we have been listening in quiet places, turning pearls in the light and searching for imperfections too small to see. But particle physics is also a theatre of noise, where beams of protons crash together at nearly the speed of light, and detectors the size of cathedrals record the shrapnel of creation. If EDM experiments are like meditation, colliders are like symphonies played at maximum volume. Both aim at the same question. What hidden rules shape the universe, and what tilts gave matter its victory over antimatter? At the edge of these colliders, hints have begun to appear, faint, like shadows cast before the dancers themselves step onto the stage. The Large Hadron Collider at CERN, the most powerful machine humanity has ever built, has not yet found the dramatic discoveries many once hoped for. No supersymmetric partners, no extra Higgs fields, no new dimensions peeking through. But in its patient accumulation of data, it has begun to reveal subtler signs. In 2025, the LHCb experiment reported something striking: the first hints of CP violation in baryons. For decades, CP violation was observed only in mesons, particles made of a quark and an antiquark. Kaons in 1964, B mesons in the 1990s, those were the stages where the asymmetry danced. But baryons, particles made of 3 quarks like the protons and neutrons that fill our universe, had long kept their secrets. To see CP violation, there is to glimpse the asymmetry, entering more directly into the very class of particles that make up matter itself. It is as if the whisper of imbalance had stepped closer, from the periphery of exotic mesons to the heart of the particles that build galaxies. The measurements are still tentative, their significance not yet at the gold standard physicists require. But even a whisper is enough to stir hope. If confirmed, it would mark a deepening of the story, a sign that the imbalance is not confined to rare corners of the particle zoo, but touches the very essence of what we are made of. Alongside this, another hint comes from a different kind of experiment. T2K in Japan, where beams of neutrinos are fired across hundreds of kilometers to underground detectors. Neutrinos, those ghostly seeds from our previous session, may also carry CP violation. If neutrinos oscillate differently than antineutrinos, it could be another path to explaining the survival of matter. Early results suggest such a tilt may indeed exist, though once again the statistics are not yet strong enough to declare victory. Still, the possibility that neutrinos carry their own asymmetric whisper ties beautifully into leptogenesis. The idea that the seeds of imbalance were planted in the lepton fields before flowering into baryons. And then there is supersymmetry, still lingering at the edge of the stage like a promised performer who has not yet appeared. Susie, as it is affectionately called, remains appealing for many reasons. It balances the equations of the Higgs field, stabilizes the vast hierarchies of scale, and in its symmetry predicts partners for every known particle. More than that, supersymmetry naturally introduces new sources of CP violation. If any of its superpartners had been found, the path to baryogenesis might have been clearer, but so far the stage is empty. We see no squarks, no sleptons, no gluinos. Only shadows remain, dancing in theory but not yet in experiment. And yet physicists do not give up. The history of discovery is one of patience rewarded. The Higgs boson itself was predicted in the 1960s but not found until 2012. Gravitational waves were predicted by Einstein in 1916 but not detected until 2015. To wait decades, even lifetimes, is part of the rhythm of science. The absence of Susie at current energies does not mean it is not real. It may simply be waiting in higher reaches we have not yet climbed. There is a certain poetry in this stage of physics. We stand between silence and hints, between the meditative patience of EDM experiments and the thunderous noise of colliders, between theories that sketch grand patterns and data that reveal only fragments. It feels like sitting in a theatre where the curtains rustle but do not part, where the shadows move behind the scrim but the dancers do not yet emerge. We know the performance is there, we feel it in the floorboards, hear it in the faint shuffle, but for now we wait. What makes this wait comforting is that even the hints themselves are enough to keep the story alive. A CP violation in baryons, if confirmed, would extend the reach of asymmetry into the matter we touch every day. A tilt in neutrino oscillations would tie the faintest particles to the grandest outcome, the existence of galaxies. The appeal of supersymmetry, even without evidence, continues to inspire experiments, theories, and entire generations of students. Science is not only about the discoveries we have already made, it is about the pathways we keep open, the roads that may yet bend toward truth. So as the data accumulates and the shadows lengthen, we remind ourselves that the universe is patient, and we must be too. The hidden rules will not reveal themselves all at once, but through whispers, tilts, shadows, and songs too faint to hear without decades of listening. One day the stage may open, and the dancers may step into the light. Until then, the hints themselves are part of the performance, reminders that the play is still unfolding. There is something deeply reassuring about a pattern that repeats. When you fold a paper snowflake and open it up, the mirrored arms radiating outward feel almost inevitable, as if your hands only revealed what was already waiting there. A snowflake, drifting slowly down through the winter air seems too delicate to obey the same rules as planets and stars, yet it does. The same geometry that governs the orbits of worlds also whispers in the lace of ice crystals. In this way, symmetry becomes nature's language of calm. Symmetry, at its heart, is rhythm. You see it when you look at a seashell spiraling in precise proportions, or when you notice the petals of a daisy arranged in a circle that could turn and still look the same. You hear it when a song repeats its refrain, not tiring but soothing, reminding you that familiarity can be as beautiful as surprise. Even in the movement of your own body, with left and right balanced across a central line, you carry this rhythm. Without symmetry, walking might feel like stumbling, but with it, you glide. The comfort of symmetry lies in its predictability. When something repeats, you know where it is headed before it arrives. The arches of a Gothic cathedral, repeated down a long nave, invite your eye to follow them forward into a vanishing point of quiet. The tiles on a floor, though simple, create a steady grid that reassures your steps. Even in the face of life's uncertainties, these repeating shapes tell you that not everything is chaos. Some patterns hold, some structures endure. In the heavens, symmetry shows itself on the grandest scales. The orbits of planets around the sun are ellipses, repeating paths traced again and again, year after year. You might imagine Earth's journey as a circle drawn in glowing ink, retraced so precisely that it becomes a shining band in space. Jupiter, Saturn, and the other worlds each follow their rhythm too, all part of a cosmic dance that has lasted for billions of years. Even comets, wild as they seem, swing back on predictable loops, their returns like refrains in a piece of music too vast for a single lifetime to hear in full. There is something healing in this. You can look at the stars on a quiet night and know that Orion will return each winter, that the moon will wax and wane in its endless cycle, that the tides will keep rising and falling. The symmetry in these motions is a reminder that beneath the noise of daily life a deeper order persists. The universe may be vast and strange, but it is also steady. Its rules are quiet and dependable, repeating across scales from the smallest to the largest. Artists and architects have long drawn on this comfort. A Persian mosaic, with its interlocking geometric patterns, can hold your attention not by surprise but by repetition so intricate that it becomes meditative. A Bach fugue, weaving its voices in mirrored phrases, creates a calm so structured that it feels like architecture made of sound. Even a child tracing mandalas in the sand is, in a sense, recreating the cosmos, circles within circles, each one reflecting a quiet order that has no beginning and no end. Of course, symmetry is not only beautiful, it is powerful. It is the hidden reason why a snowflake forms with 6 arms instead of 5, why a crystal grows with its repeating lattice, why your body is mirrored left to right. These are not accidents, but consequences of the rules that matter follows. In physics, we say that symmetries determine what is possible, but in daily life you feel it as a kind of reassurance, the left hand mirroring the right, the horizon meeting the sea in a line so straight it seems eternal. Sometimes people ask why humans are drawn to symmetry. The answer may be that it is the natural language of the universe itself. When you encounter a balanced shape, you are not just seeing design, you are recognizing kinship with the laws of nature. Your eyes linger on a butterfly's wings because the same rules that shaped them shaped you. Your mind finds rest in a pattern of music because your neurons themselves fire in rhythms. Symmetry calms us because we are creatures born inside its web, and yet there is another layer of comfort here. Symmetry is not fragile. Even when the world feels uncertain, even when history bends and life surprises, symmetry is always there in the background, holding steady. The earth may shake, storms may pass, civilizations may rise and fall, but the sun will still set and rise, the constellations will still spin overhead, and a snowflake will still fall with 6 arms of frozen grace. Symmetry is the lullaby the universe sings, and we are fortunate enough to hear it. As you let your thoughts drift tonight, you might notice symmetry in the smallest places. The way your breaths in and out match one another. The way your heartbeat finds a rhythm that repeats. The way your body rests evenly on the bed. These are echoes of the same patterns that govern galaxies. The language of symmetry does not belong only to stars and atoms, it belongs to you too. It speaks quietly, but always in rhythm, always in balance, and in that rhythm you can find rest. If symmetry is the language of calm, then imperfection is the language of possibility. It may seem counterintuitive at first. A flawless mirror, a perfectly balanced shell, a melody that repeats forever. These feel serene. But if the world were made only of perfect repetition, there would be no change, no story, no you or me to marvel at its order. The paradox of the universe is that its beauty comes not only from symmetry, but also from its breaking. Think of a potter shaping clay on a wheel. As long as the clay spins smoothly, the vessel remains perfectly round. It is pleasing, but simple. The moment the potter's hand presses just slightly more on one side, the symmetry shifts. The pot widens here, narrows there, and suddenly it is not just a circle. It is a cup, a jar, a vessel with purpose. The break-in of symmetry transforms potential into form. Without that break, the clay would stay a lump, elegant in balance perhaps, but without character. The same principle runs through nature. Consider your own body. From a distance, you appear symmetrical. 2 eyes, 2 arms, 2 legs. But inside, the illusion of perfect balance fades. Your heart tilts to the left, your liver hides on the right, your brain itself shows subtle asymmetries. If your body had been perfectly mirrored, it would not function. Life requires a tilt, a preference, a departure from absolute balance. It is precisely because symmetry breaks that we live. On a grander scale, this breaking is written into the cosmos itself. In the earliest moments, the universe may have been a uniform sea of energy, a perfect symmetry of matter and antimatter, forces indistinguishable from one another. For a moment, it was a song sung in unison. But then cracks appeared. The forces separated. Gravity pulled away. The strong force claimed its realm. The electro-weak force later split again into electricity and the weak nuclear force. Each break was like a note diverging from a chord, adding harmony, richness, and complexity. What was once a single tone became music. Even the galaxies owe their existence to imperfection. If the Big Bang had been perfectly smooth, matter would have spread evenly like fog, leaving no clumps, no stars, no planets. But in the faint ripples of the cosmic microwave background, we see the fingerprints of asymmetry, tiny overdensities that gravity later sculpted into galaxies, stars, and eventually the Earth beneath your feet. It is comforting to remember that every atom in your body traces back to a universe that wavered ever so slightly from perfection. Without that unevenness, you would not be here to breathe, to dream, or to wonder. Art also finds its soul in imperfection. A Persian rug, woven with exacting care, will often include a deliberate flaw, not as a mistake, but as a tribute to the idea that perfection belongs only to the divine. Japanese pottery, when cracked, is sometimes repaired with golden lacquer, highlighting the break rather than concealing it. This practice, called kintsugi, does not see the fracture as a failure, but as a chance for new beauty. In both cases, the lesson is the same. Wholeness is not found in flawless symmetry, but in the dance between order and disruption. In music too, symmetry alone is not enough. A song that repeats the same phrase without change soon becomes dull. What gives music life is the deviation, the unexpected chord, the variation in rhythm, the breath of silence between notes. Listeners lean in when something shifts, when the symmetry bends but does not collapse. The moment of difference creates tension, and tension births meaning. You can sense this principle even in daily life. The comfort of routine comes from its symmetry, but the memories you cherish often come from the unexpected. The time the train was delayed and you discovered a hidden cafe. The evening when a storm broke the pattern of the week and left the air fresh and new. The days when everything did not go as planned, and yet those very breaks became stories worth telling. Symmetry soothes us, but its breaking makes us alive. This is why physicists speak of symmetry breaking not as a loss, but as creation. When the weak force revealed itself as different from the electromagnetic, it was not a flaw in nature's design, but the next step in its unfolding. When matter won out over antimatter, it was not a betrayal of balance, but the very reason galaxies could ignite and persist. Breaking symmetry is how the universe moves forward, how it escapes stillness, how it makes space for novelty. So when you look at a snowflake, admire its sixfold symmetry, but also remember the tiny imperfections that give each flake its uniqueness. When you hear a melody, notice the repetition, but also the small variations that keep it alive. When you gaze at the stars, know that the galaxies you see were born from ripples, not from a smooth sea. Perfection is calm, but imperfection is creative. And perhaps this is a lesson for us as much as it is a law of physics. We may strive for balance, for order, for symmetry in our lives, but it is often the cracks, the unexpected detours, the mistakes, the moments of imbalance that give us shape. Like a pot tilted by a hand, like a star born from a ripple, like a crack filled with gold. Our imperfections are not merely flaws. They are the beginning of form, the place where possibility enters. When we look back across the long arc of the universe's story, it is tempting to think that all the great breaks have already happened. The forces split, the imbalance between matter and antimatter was struck, galaxies formed from ripples in the ancient glow, and stars kindled to make planets and life. It might feel as if the work of symmetry and its breaking is done, like an artist who has set down the brush and stepped away from the canvas. But the universe is not finished. It is still cooling, still expanding, still carrying possibilities folded within it like verses of a song not yet sung. Symmetry has always been more than a relic of the past. It is also a guide to the future. Physicists suspect that the rules we know are not the final rules. Just as the electroweak force once appeared unified but later separated into the electromagnetic and weak forces, there may be deeper layers still hidden, waiting to be revealed under energies we cannot yet reach. In this sense, the cosmos may still hold further transitions, further breaks in symmetry that will reshape the way we understand reality. Imagine the universe as a vast orchestra, each section representing a force. In the earliest moments, they all played the same note in unison, so pure it was almost a hum. Then the sections began to peel away, strings taking one theme, brass another, percussion adding rhythm. What we hear now is a complex symphony of forces, each with its own melody. But perhaps more instruments remain backstage waiting for their cue. When the time comes, another harmony may join, altering the entire sound of the performance. One possibility physicists dream of is the unification of the known forces with gravity, a grand unified theory that could reveal an even deeper symmetry. At present, gravity stands apart, immensely weak compared to the others, like a drum so faint it can barely be heard beneath the orchestra. But maybe, at some higher energy, or in some future transition, gravity too will join the music, and the score of the universe will sound more complete. The idea that the universe may still harbour undiscovered symmetries does not mean it is unstable. Rather, it is like a river flowing quietly forward. The surface may appear calm, but beneath, currents continue to shift. New patterns may surface only after long stretches of time. For now, we live in the aftermath of the great breaks that made us possible. But to believe the story ends here is to underestimate the creativity of the cosmos. Already, experiments continue to probe these questions, listening for the faintest echoes of new rules. If the universe has another phase transition ahead, it might reveal itself in subtle signals, ripples in space-time, unexpected patterns in cosmic radiation, or even new particles flickering into view. The search is not just for novelty, but for understanding, for a sense that the song we hear is not only beautiful, but also part of a grander composition. And even if the universe itself does not undergo further dramatic changes, our understanding of symmetry will evolve. Each generation uncovers new ways to see the same patterns. What seemed absolute a century ago is now seen as partial, provisional, awaiting refinement. The rhythm of discovery itself is a kind of symmetry. Questions followed by answers, answers unfolding into deeper questions. It is a song of curiosity that has not yet reached its refrain. In art and life too, the future of symmetry remains open. Architects will continue to find new ways to balance harmony and asymmetry in their designs. Musicians will play with repeating structures and their creative distortions. The search for balance is never finished because each context reshapes what balance means. The cosmos is not unique in this. As long as there are new patterns to notice, new fractures to cherish, the song of symmetry will keep growing. For you, listening now, the thought may be both humbling and comforting. The universe did not stop creating once galaxies formed. The same creativity that gave birth to stars continues quietly, invisibly all around us. Each breath you take participates in a balance between oxygen and carbon dioxide. Each heartbeat relies on an asymmetry of electrical signals. You're part of this ongoing story, an unfinished verse in a poem that stretches across billions of years. So perhaps the future of symmetry is not only in the stars or in the hidden laws of physics. Perhaps it is also in how we live, how we balance our days, how we learn to accept both the calm of order and the gift of change. The cosmos may still hold surprises, but so does a single human life. To live is to feel symmetry, and it's breaking again and again in ways small and large. And when you think of the future, you need not imagine it as a final answer. Instead, you can picture it as a melody waiting for its next verse, already humming faintly, just beyond hearing. The universe, like a song not yet finished, will continue to write itself in rhythms of symmetry and breaks, in repetitions and surprises. You do not need to know every line. It is enough to listen, to rest in the music as it unfolds, and to trust that the rules, whether calm or fractured, will carry on.